Hi everyone. So today we are going to solve a very popular problem using recursion. So let us hear the problem. So it says that we have been given an integer array containing, let's say, n integers. Okay, and this integer array, it represents a set. What is the meaning of a set? So set means a collection of distinct elements. Okay, so in a set it can never happen that two elements are exactly the same. Okay, and here, because it is going to contain all the integer elements, so basically I can say that this array is an array of distinct integers. There are no duplicates inside it. Okay, cool. So let us take a quick example. So I can have an array that looks like this. Okay, distinct elements, right? Now what I am supposed to do is that I can treat this as a set, and now I am supposed to generate all the subsets of this set. Generate all the subsets of this set. Cool. So guys, I would ask you people to take a pause of maybe 1 minute and think that if the set contains n distinct elements, then how many distinct subsets can it have? Okay, so just think about this. Think about it, that there are n distinct elements, so how many distinct subsets can it have? And also list down those distinct subsets for this particular input. Okay, so let us all do that for 1 minute. Cool. So let us answer the question of printing all the unique subsets for this thing. Okay, so if you take a look over here, first subset can be this entire set itself, because a set is a subset of itself. And then I can have something like 1, 2. I can also have 1, 3. I can just have 1. I can have 2 and 3. Just 2. Just 3. And then there is an empty set also. So if you take a look over here, there are 8 of them. Okay, so corresponding to this set, there are 8 distinct subsets. Cool. Now let us try to understand one thing over here, that with respect to these subsets, if you take a look at any one of them, let's say you take a look at 1, 3, then would you want to generate something else which is 3, 1 and call that, hey, this is yet another subset of this set? No, that is not right, because this is nothing but a permutation of this only. So it is not allowed. Now this is very important point, right? So two subsets would be different from each other. Let's say 1, 2 and 1, 3 would be different from each other if at least one element is there which exists here and does not exist here, and vice versa, right? But in case of this and this, they are nothing but permutations of each other. You understand permutation? So if you jumble up the numbers in an array, just jumble up their positions, swap their positions randomly without introducing something or without deleting something, then what you get is a permutation, right? So that we do not want, because this would be treated as a duplicate subset of this. Similarly, if let's say you have 1, 2, 3, please do not generate 3, 2, 1 or 3, 1, 2 again. This is a really important point to be kept in mind. Okay, cool. Yeah, so this particular input had 8 distinct subsets which are represented over here, right? Cool. Another thing that I asked you guys is, how about solving this problem for a generic case? So let's say there are n distinct elements in my set. So how many subsets can I have? So if you take a look, let's say your elements are A0, A1, A2, so on till an minus 1, which is the last element. Now, think in the manner of inclusion exclusion. This thing helps a lot in solving the problems where you have to generate all the combinations and things like those, right? What do I mean by inclusion exclusion is, let's say I generate this much of space, okay, and then I try to make decision for any element. Okay, so let's say you are currently at this element. how many choices do you have with respect to this element? I mean, if you have to generate a subset, what all are the things that you can do to this element? So there are just two things. You can either have it or not have it. Okay, so there are just two choices corresponding to it. Similarly, for this also two choices, for this also two choices, for this also two choices. And remember that those two choices are distinct from each other, because saying a yes and taking this is different from saying a no and not taking this, right? Because all those subsets which will contain a naught, so let's say this is category 1 which contains a naught, and then they have something, I don't know what they are, will be different from the other category which does not contain a naught and contains something else, right? So you can again think here just like recursion. Just think of it in a way that you start your journey with an empty set, right? And when you start your journey with an empty set, then at the level of any element, you have got two choices. You can either take it or not take it. If you take it, then the state of this set changes, because now this will contain a naught. And if you do not take it, then it will not contain a naught. And what will happen next? Once you have made your decision for a naught, so now you would want to make your decision for the remaining part of the array, right? So this is how it is going to look like. So whatever I said, just ponder over it for few moments, and then think that how many variables do you need to represent a state of a recursive function call, and how does the recurrence relation look like, and what would the termination condition be. Once you have thought that much, then also think that how the recursion tree diagram is going to look like. Okay, so take a pause of 2 minutes and maybe more than that, and then think about that. Do this piece of work on your pen and paper. Okay, cool. So those of you who would have done this piece of work might have noticed the answer for this question, that if there are n distinct elements, then how many distinct subsets are going to be there? Because everywhere, for every element, there are two choices. For every element, there are two choices. So what is the total number of choices that I have in all? So it will simply be the product of this, using the rule of product from combinations, right? So what will it be? It will be 2 raised to power n. Okay, so like if you take an example of this is the result of saying yes, yes, yes. You said yes, yes, yes for all the elements, so you had this. This is the result of saying no, no, no. This is the result of saying yes, no, and then yes, right? So selection and rejection are like yes and no respectively only, right? So if you think in that terms also, then corresponding to every element, you can either have a yes or no. And since there are n such elements, so total number of choices will be 2 raised to power n. So this is a generic thing which all of us should remember, that if there are n distinct elements, distinction is very much important. The elements should be distinct. If there are n distinct elements, then the total number of distinct subsets will be 2 raised to power n. Think, will the answer still be 2 raised to power n if the elements are not distinct? No, it will not be. Okay, and we'll do one such question later, but you can again take a pause of 1 minute and think that in such case, will the answer be 2 raised to power n or lesser than that or more than that? What? Okay, cool. So let us try to generate all the possible distinct subsets for this given set, which contains 1, 2, and 3 in it. Okay, cool. So guys, how do I go about it? So as I said, you'd want to always start your journey with an empty set, right? And now you can start with either the first element or the last element. It's totally up to you. Okay, let's say I wish to start with the first element. Okay, so currently I want to make a decision for first element. How do I recognize first element? By passing the index of it. So the index of it is 0. There is a function call that contains an index about which the decision has to be made, okay, which will help me for calls to the next states, whether I have taken that element or not taken that element, right? And then there is this set which evolves as and when my decisions are made, whether to take something or reject something, totally based on that, right? So currently I'm at 0th element. I can either reject it or accept it. So rejecting means not taking it. So N means not taking it. Y means that yes, I am taking it. Okay. So if I say a no about this element, what will happen? Will my subset change? It will not change, right? So my subset will remain as it was, right? And how about my index? Now the index should grow. Why it should grow? Because now you are done with your decision for the 0th element. So now you must move on to the next element, which is at index 1. Okay, cool. But let's say had you taken it, if you had taken this element, then your subset would have contained 1, okay, and then you would have moved on to the next element, which is at index 1, right? Cool. So first, definitely this recursive call will be finished, then the control will come here, and then this recursive call would be made, right? Cool. So let us keep going on from here. So you should realize one thing for sure, that at level 0 you are making decision for 0th element. At level 1 you are going to make decision for first element, and so on. That is how you will keep saying this thing. Okay, now again here you are at index 1. Again you have got two choices. Either you can have this included or you can reject it. So if you reject it, then how is it going to look like? If you reject it, then after rejecting it you will move on to the next element, which is at index 2, and your subset still looks like this. But had you selected it, then you would have got this element with you, and then you would have moved on to the next particular index, which is index number 2. Now again here you are at index number 2, which is 3. So again you have got two choices. Either you cannot take or you can take. Okay, so if you do not take, what happens? That your set remains as it is. And now what does the meaning of 3 is? This is the index of the array. So 3 means you have hit the end of the array. So the moment you have hit the end of the array, you have got no elements left for which you can make any decision. So basically that marks the end of your recursion. So this is your termination condition, right? So basically corresponding to this termination condition, you will be printing this thing, which is nothing but an empty subset. And this empty subset is a consequence of the choices that you made. Okay, because you said no for 0 index, you said no for index 1, you said no for index 2. That is the reason you do not have anything with you, right? Cool. Okay, now once this is over, the control comes back to the parent, and now parent will make the yes transition. Yes transition means it would want to have the element at index 2. So the element at index 2 is 3. So it will have 3 with it, and now the index will grow to 3. When that happens, then again this is the end of my recursion. So how do I recognize end of my recursion? Based on the value of index. So the moment the index becomes equals to n, it simply means that I have already covered a path starting from, the first element till the last element, and I have decided for them. It could be a sequence of yes or no, right? So that is how I have got my job done. So corresponding to this, you would be printing this. Okay, and this is again a consequence of your choices, because you said no, no, and yes. You said no, no for these first, and yes for the second one. Okay, if you take a look here, okay, now what will happen when this is over? So the control will transfer over here, and now you will make a yes transition. Okay, so once you make a yes transition, corresponding to that, what happens? Corresponding to that, in this empty set, you would want to have this first element. Okay, and what is the first element at index 1? That is 2. That is the reason I have 2 over here. Now again, when you are here, you again have two choices, no or yes. So you are at index 2, which is element 3. You have two choices. Either you can take it or not take it. So if you do not take it, you will move on to third index, and you will just have 2 with you. And again, this is your termination condition. In the yes case, you would have opted for the element at index 2. So if you would have done that, your subarray would look like this, and now this would be your, again, a termination condition. Cool. So that is how this would also expand. So take a pause of 2 minutes and then expand it on your own if you have not done it yet. Cool. So as you might have observed, again, see, the rule is very simple. The recurrences are very simple. No or yes for any element at a particular index, either no or yes. So if you say no, you move on to the next index, which is next element, and your subarray still looks like that. But had you said something like yes, in that case, along with 1, you would have got the element at index 1, which is 2, and you would have moved on to index 2. Okay. Now again, you are at index 2 over here. So again, you realize here you made decision for the index 0. Here for all nodes you made decision for index 1. Here for all nodes you're going to make it for index 2, right? Cool. So now you are at index 2. This is your index 2. So if you say no, then you would move on to the next index, and your subarray will just have one in it, and based on this you will terminate and print this up, right? And again, this is consequence of your choice. Yes, no, no. Okay, so you just said a yes for this, and then for these two you said no. Okay, and the choice was to call yes. If you say yes, then you would want to have this element which is at index 2. So at index 2 you have got 3 with yourself. So this is how the subarray would have looked like. Now the control transfers here, this is done, so this will exit, so control transfers here. So now it will invoke this. When it invokes this, what would happen? So initial state was this, and now it would want to include, it would want to say yes for the element at index 1, which is 2. So it would have 1, 2 over here. Now again here you have got 2 choices for this index, no or yes. Index 2, I have got 3. If I do not include it, I just have 1, 2, and then I move to the end of the array, and this is how I terminate, right? And if you say yes, on the other hand, if you say yes, then what is going to happen is that you would reach the end of the array and you would have this thing with yourself. Okay, cool. So now take a pause of 2 minutes and think that how you can actually convert this into lines of code. So just think about that. Cool. So you must have given a proper thought that how to convert it into lines of code. So whenever you are going to write a recursive code, what are the things that you want to have? So first thing that you would want to have is your termination condition, which is easy to determine. The moment you see that your index, which always grows by 1 unit, the moment you come down, your index becomes index plus 1. So the moment it becomes n, that means you are out of elements now. So you have made your choices and that choice is reflected in this. So you'd print it and you will simply exit, right? The other thing is your recurrence relation. So this is the logical view of your recurrence relation. So whenever you are at ith index, you can either choose to not have it in your array, in your subset. So if you do not choose to have it, this is not going to get affected, just this will change. And if you choose to have it, this will change for sure. This always changes. This index always changes the moment you come down. But in corresponding to yes transition, this will also change because you will now insert the element ai in this subset, right? So this is how you can think of writing your recursive code. Now tell me one thing. So here, would you want to create a new copy of this array and then pass it here and create a new copy of it, put 1 inside that copy and pass that copy here? Would you want to do something like that? Because think of it in this way. If this is just pass by reference, which actually we would want to save space, we have to do pass by reference, because if you do not do pass by reference, then every time a new copy is going to get created, in that new copy the elements would be copied one by one, so it would raise your time as well as space complexity. So can I do it by just using an array which is simple pass by reference? So the answer is yes. Just try to understand. So what would have happened, the process would have started from here, you would have said no, so just the index changes, this does not change. Again no, just the index changes, this does not change. Again no, just the index changes, this does not change. And then when this is over, you would have come here, you would have said yes for this. Once you would have said yes for this, so at this particular index location, whatsoever it is, at this particular index, you would simply have put, okay, the value at index 2, which is 3. So you would have inserted 3 over here, right? Now when this terminates, the control comes here. This also terminates, the control comes here. So now what would you do is that the position where you had placed 3, you would want to override by placing 2. This is a very important thing to understand. Okay, and the question that we did previously in the previous lecture, there we learned about it, right? That how I can just use a particular it was a character array. In that case here it is an integer array. How can I just use it and just somehow manage to override the characters? Okay, so I can just change this 3 to 2 over here. But for that, what is it that I need to track? In other words, how do you decide that at which index, let's say you are here, okay, and this is index 2. So at index 2 you have got 3. So in this particular subset, at which index this element is going to get inserted? How do you get to know that? So think about it for a while. Just pause the video for a while and then think, how would you get to know that at which index in this particular subset 3 is supposed to get inserted? Do you need to track size of it? Just think for a moment. Cool. So you might have guessed it very easily, right? So if the size of it is, let's say, x, if the size of it is x, that means that I have got elements a, b, c in it, right? So the size x here is 3. So the next element whichever should come at index x, which is 3, right? So if I simply just track the size of my subset, let us call it, because this is an array, so let us call it an auxiliary array whose initial size is, let's say, 0, because the size here reflects the number of elements that I have intentionally pushed into this array so far. So to start with, when I make the call, I just pass it as it is without inserting anything. So I can treat it as something whose size is 0, okay? And the moment I push something in it, okay, the size of it becomes size plus 1, okay? So although I have not written a separate size variable over here, but that is very much required, right? So I would have a size variable which would be like 0 over here, okay, which would again be like 0 over here, again be like 0 over here. So when does the size change? The size changes the moment you push something into this array, okay? It becomes size plus 1. So again, this is a no transition, so it would have been 0. Here you would have pushed into this 3, okay? So the size would have become 1, right? Now let's say when this gets over, control comes here, this gets over, control comes here. Then now, since it knows the size, so whatever it will push, which is at index 1, which is 2 actually, that would get pushed at index 0. So initially at index 0 I had 3, but now this yes transition, which tries to place 2 at index 0, would override this 3 to a value 2 and then again increase this size to 1. So can you think whether this size variable should be passed by value or passed by reference? So this should be passed by value, right? Because I don't want this size to get reflected over here or here, because had that been the case, you would have tried to push the element at index 1, which is 2, at index 1, right? So size is the size variable which tracks the size of this, which is nothing but the elements pushed by you consciously into this array, is a simple pass by value. Similarly, the index is also a pass by value, right? Just this is something which is passed by reference, okay? So now that you have understood this much, now give it a last shot or something. Take as much time as you can to write a simple code, okay, which does exactly what I have said and then generates all the subsets of a given set. Cool. So let us all understand. So first let us think, what should be the return type of a function? So I do not need to return anything, right? I just need to print the values and then exit, right? So it should be a void function. And let us name our method as print all subsets, okay? So this print all subsets method, now think what all are the arguments that I need to pass to it. Think on your own. So first thing is I need to pass the array. See, this array is not going to change. By the way, this is not going to change. So either you can have it declared globally or you can pass it. but this is not going to change, so this is not going to determine the state of your function call. So let's say if you are passing it, so you would want to pass this array. So this is your actual input array, this is not your auxiliary array, this is your actual array. Okay, so you'll pass this, and along with this you will pass the number of elements that are present in this. Okay, and then you would pass the index, which means the element of the array which you are talking about, right? And along with this, then you would pass the auxiliary array. So let me call it a temporary array for now, because this acts like temporary array. And then I'll pass a size variable. Okay, so this size variable basically tracks that how many elements I have pushed in it so far. So this array is your input array, n is the size of your input array, I denotes the element whose fate you will decide at this level, temp is your auxiliary array, which will be used to pass it by reference across function calls and generate all the possible subsets, and size simply tracks the number of elements that have been pushed in it so far. Okay, so cool. Now let us understand how the code would actually look like. Okay, so what should be my termination condition? I should terminate the moment my index has reached the end of the array, which is n. Okay, before this, one question that you should ask to yourself is that because you are going to declare an array temp and then pass it, so whatever will be your main driver function, that there you will declare this temp and pass this temp from there by reference. So what should be the size of this? Because this is an array, so you would want to initialize it with a particular size, right? So what can be the maximum size of subset? The total number of elements in the set, right? So the maximum size of this can be n. So make sure that when you initialize it with the size of n, because if you initialize it for a smaller size, you might get index out of bound exception. Okay, cool. So I will terminate at these cases wherever I see that my index I has become n. In this case, what will I do? So I'll print the contents of my temporary array. That is the first thing that I'll do. Print the contents of temporary array. I think you can easily do that. And after that, you should simply return. Okay, after that, you should simply return. Otherwise, what are the choices that you have? So just think of it. What are the choices that you have? So here your first call was no and then second call was yes, but it can be vice versa also. It's totally up to you. Okay, so you can first have a yes transition and then have a no transition. Okay, so what you will do corresponding to yes transition, let us try to write that. Corresponding to yes transition, you would want to include an element in the temporary array. Now, at which index of the temporary array would you want to include it? So you would want to include it at size index. So you would do temp of size equals to what? You're talking about the ith element of this array. So temp of size equals to array of I. And once you have done it, then you will call this thing recursively corresponding to your yes transition. So what would happen is array would be passed as it is by reference, the size would be passed, and the index. So the moment you come down, your index becomes I plus 1. Okay, and then you pass your temporary array, and because you have inserted a new element at at size index, okay, so the new size will be size plus 1. Okay, now what about no transition? What is going to happen in no transition? Are you going to modify this array? No, no need to modify it, because the values will get overwritten as I had explained it before, right? So what you can do is you can just pass the things as simply as this. You need to always move on to I plus 1, whether it was a yes or no transition, pass temporary array as it is, but just keep the size same, because corresponding to no transition, the size does not change. The size only changes corresponding to yes transition. Okay, cool. So this is all about the code of it. Now I would like you guys to just run it and then see how, maybe try to draw its recurrence tree diagram on your own and then examine it thoroughly, make some changes, play around with this, print the values at multiple levels of recursion and see what is actually going to happen. Okay, if you want, you can actually do that. You can print the values at in all the recursive calls. So the moment the call comes over here, you print the contents of the temporary array. Okay, how do you decide that how much portion of the temporary array you have to print. For that you have got size, which tells that from index 0 to index size -1 you have consciously placed the elements. So just print that much. Okay, cool. Now let us understand how much the time complexity of this is going to look like. So if we understand that thing, how many leaves will be there in this tree? This is again a binary tree. How many leaves will be there? So can I say that the number of leaves will simply be equal to 2 raised to power n if there were n elements, right? Definitely it will be there because every leaf corresponds to one particular subset and there are 2 raised to power n subsets, right? Okay, so these many function calls will be there at the bottom. Okay, how many function calls will be there above it? So because 2 child belong to one parent in a binary tree, so number of nodes above it will be half of this, which is 2 raised to power n-1. Above it, half of this, which is 2 raised to power n-2. So it will be like this, which will start from 1. From 1 it becomes 2, then 4, and this is how it looks like. So whatever will be the sum of this, that would be the total number of function calls, not the time complexity. That will be the total number of function calls. So this is like a standard GP, and if you use the GP formula, then you will get something like this. So the GP formula is A, which is your first term, into constant ratio raised to power number of terms -1 upon r -1. So here my first term is 1, my common ratio is 2, number of terms is, because I started with 2 raised to power 0 and came to 2 raised to power n, number of terms is 2 raised to power n plus 1 -1 upon 2 -1. So this is nothing but 2 raised to power n plus 1 -1, which is something like order of 2 raised to power n. So I can say that, hey, approximately order 2 raised to power n functions are there, function calls are there. And now what is the maximum amount of time spent at any function call? So although for these function calls, it was just order one thing that you did. You just came here. See, print got executed only for these nodes. But these nodes make up for the maximum number of nodes. In fact, half of the total number of nodes that are there in the tree. So if you take a full binary tree, you will see that in the leaf node, the count of nodes is equal to half of the total number of nodes in that binary tree, right? And that is how I approximated this thing to 2 raised to power n, right? Because total number of nodes was something like twice of it. That is getting reflected here also, right? So what is the maximum amount of time that you spend at any node? So for these nodes, you just do order one thing, which is order one assignment, and then you make the 2 function calls, okay? But for these nodes, you do a print task. And what is the maximum time that a print task can take? So it depends upon the size of the array. And what can be the maximum size of the array? By array, I mean temp array, order n, right? So the complexity would be something around 2 raised to power n into n. This is my complexity. You can also add times, because this 2 raised to power n will be much larger than this n for, high values of n. So you can ignore this at times, okay? So this is an exponential algorithm, okay? And the time complexity is very high, but you can't do anything about it, because if you are supposed to print all the 2 raised to power n subarrays, 2 raised to power n subsets, then there is no way other than printing them out, okay? Cool. So think more about it. Think if you can solve this problem iteratively. Is there an iterative way to do it using for loops? That's an interesting question that you should ask to yourself, and we'll be discussing it later. Okay, cool.